Hi everyone! Today we are going to show you how you can build a real-time streaming application that processes New York City's bus data using DeltaStream. The Metropolitan Transportation Authority, more commonly known as the MTA, is a corporation that is responsible for public transportation in New York City. Using Google's General Transit Feed specification, the MTA has made its real-time bus data available for the public. So for our use case today, we will be processing this real-time bus data in DeltaStream to detect bus trips that are becoming increasingly delayed. Let's use DeltaStream's web UI to take a look at the stores we have set up. Here you'll notice that we have a Kafka store already created. This store defines the connection between DeltaStream and the Kafka cluster where our bus data is stored. If we wanted to create other stores, we could click on the New Store button. Here, we can define connections to other Kafka clusters, Kinesis, Snowflake, and other data storage systems. However, for this use case, we'll just stick with the Kafka store we have defined. By clicking on our store, we can see some details about the store and list the topics that are in this Kafka cluster. The topics NYC bus trip updates and NYC bus vehicle positions are the ones we're interested in. Let's print the NYC bus trip updates topic to see what our data looks like. Notice that each record has a field called trip, which is nested fields for ID, date, and route. This field can identify a bus on a particular trip. There's also a timestamp field and a delay field. The timestamp field describes the epic seconds for this trip update event, and the delay field represents how many seconds behind schedule the bus currently is on its route. Let's also print and quickly analyze the NYC bus vehicle positions topic. We can see that this data contains the same trip and timestamp fields as the other topic. However, this data also includes a position field, which captures a bus's current position at the time of this event. Both of these topics we just observed follow the Google General Transit Feed specification for updates and positions. We also want to note that there was some setup involved to capture this bus data and write it into the Kafka topics we just printed. But we won't be covering that in this video. However, you can find a link to our associated blog post that covers this setup and contains any relevant links and information in the description below. Alright, so getting back to our use case. The next step is to create streams for our two data topics. We can do this in the SQL Editor tab. In this statement, we are defining a stream for our trip updates data. The fields we are defining here match the data we just observed when printing the Kafka topic. We also specify the topic that is backing the stream in the with clause. By running this statement, this stream will be created in the DB database and public schema that we've already set up. We can run a similar create stream statement for our vehicle positions data. Now that we have our streams defined, we can get to our processing logic. We're going to run a couple of create stream as select queries to refine our raw data. These will be long-lived continuous queries that ingest data from our newly created streams, perform some simple processing, then write the results into a new stream backed by a new Kafka topic. As you can see, this query is just a simple projection that formats our timestamps from epic seconds to a more human-readable timestamp format. Let's run this query. Here, we are doing the same, but for the vehicle positions data. Next, we'll write a query to detect when a bus trip's delay is increasing. So this query is another SaaS query, and it's quite a long one. We have a blog post that explains this query in depth, which you can see in the description below. But to quickly summarize this query, we are performing pattern recognition on our refined trip updates data to look for bus trips that have increasing delays. As you can see in the projection, we are writing records to our new stream that include the trip, start delay, and end delay. The start and end delay fields come from the match recognize statement in the from clause. In the match recognize, we are defining a pattern, A, B, C, and only a sequence of records in the source that match this pattern will result in an output to our new stream. A is defined as a bus trip with delay greater than 0. B is defined as the same bus trip, then having a delay of 30 seconds longer than A's delay, and C is defined as the bus trip having a delay of 30 seconds longer than B's. Essentially, if a trip is delayed, then the next update it is 30 seconds more delayed. Then the next update it is delayed by another 30 seconds. We want to write a record to our sync stream. As a next step, let's say we want to find the bus positions of delayed bus trips when those delays were increasing. We can write another CSAS query to join the trips delay increasing stream that was the result of the previous query with our bus positions data. As you can see here, our joining condition is when the data from both sides have matching trips. This is what we call an interval join, because the data from the left side of the join is looking to match with data events on the right side that have a timestamp within 3 minutes of its event timestamp, and vice versa. In this query, we are specifying the event timestamp of the delayed data events to be average timestamp. This average timestamp is the middle point of when the bus trip's delays were noticed. So we are essentially looking for the position of the bus within 3 minutes of this middle point. Let's run the query. Now, the final stream in our pipeline will contain real-time data for buses that are becoming more and more delayed, as well as the positions of these buses when those delays were happening. Let's see the full pipeline of data by going over to the Stream 360 tab. Here we can see how the data flows. We have a query reading from each of our sources, which cleans up the raw data and converts the epoch seconds to a timestamp field, resulting in the trip updates and vehicle position streams. Next, we have a query that reads from trip updates and performs a pattern recognition to identify bus trips that have increasing delays. The result of that query is joined with the vehicle positions data to get our final results stream, delayed trip positions. Let's go back to our store so we can print out the topic backing our final results stream. As you can see in the results, you can track the positions of a particular bus trip. Using a simple Python script, we can plot these points to give a visual representation of where the bus trip was. Over time, the MTA or other transit organizations can collect these data points and see if there are any patterns to traffic delays. This can help them potentially optimize bus routes or inform traffic-related decision-making. For transit goers, getting this information in real time is really important so they can make decisions about how they want to get to their destination. It can be very stressful to wait for a bus that is going to be much later than the estimated time. And this unknown additional delay can cause people to miss their connections, trains, flights, and other modes of transportation, causing even a greater delay. With just a few queries from DeltaStream, we were able to take the MTA's real-time bus data and write a streaming application to detect buses that are becoming increasingly delayed. If you'd like to read more about this use case, a link to the video's associated blog, along with a trial to DeltaStream, is found in the description below.